Hello, my physics friends. Mr. Consolino here for our first physics video and our first topic. And we're going to be talking about one-dimensional kinematics today and how we can do a verbal description of motion. Before we begin, though, we need some background. We need to know, what is this thing that I'm calling kinematics? I've never heard it before, or maybe I have, and I don't know what it means. Well, all kinematics is it's the study of motion. But for right now, it's only that. We're only looking at the motion after it was started. We don't really care how it got started. We only care about the motion itself. So let's say in this example, I am walking down and all of a sudden I start falling down the stairs. Kinematics in this case is going to be studying the motion of me falling down the stairs. However, we don't care that the reason I fell down the stairs is because maybe my sister tripped me and that's why I'm falling down the stairs. All kinematics is the study of that motion after it's started. For right now, we're only going to be looking at one dimension, and that just means things moving in a straight line. So maybe it's Mr. Consolino right here. He's walking, he's got some good hair. Maybe. I don't know. As you can tell, my drawing skills are not great, and I'm walking in a straight line because I don't run, I just walk. And I'm walking to the left and I'm just strolling. That's one-dimensional kinematics. Or let's say we have a ball that's falling straight down and he's falling, and we want to study how that ball is falling, but it's only moving in a straight line. So that's all we're going to study now. We're going to sort of simplify it. We're going to say we don't care about things that move in crazy, weird paths. We only want to look at things that are traveling in straight. We're also going to use what's called the particle model. And basically all this means is that instead of studying how every single particle in an object moves, we're going to say we can basically say the motion of an object is the same as the motion of that object's center of mass. So we can kind of, squish a whole object, a car, me, a ball, and we can say, you know what? The motion of Mr. Consolino is the same as the motion of his center of mass. So we're only going to look at that. And all the center of mass is where your mass is sort of centered. So like a lot of times it's going to be at the center of an object. So for a person, it's right around our stomachs. For a soccer ball, it's right at the center of the soccer ball. We're just going to look at how the center of that object moves. The other thing we have to realize is the difference between a scalar and a vector. And I'm sure some of you have already heard these quantities, maybe in one of your algebra classes, when they talk about scalars and vectors. And they have the same meaning, but in math, you get a very mathematical explanation as to what they are. Here, I'm going to try and simple it down and to give you the physics side of it. Scalar is just a quantity. It's just a number that has a number. It might have a unit, it might not. It depends on what it is. But it's just going to be a number. That's all that's associated with it. So some examples of this are distance and speed. However, you could also have temperature, or maybe, the number of eggs you bought at the store could be a scalar quantity. It's just, it's anything that's just a number and it might have a unit. It's 5 degrees Celsius outside. Okay, that's a scalar. A vector, on the other hand, is going to be any quantity that's expressed by both a magnitude, so it's going to have that number, and it will have a direction attached to this. And what that's going to look like is going to have a number, a unit, and then it also have either an angle or a plus or minus sign, or we might say to the left, to the right. It's going to have some direction associated with that. So one example of this is maybe my velocity is 5 meters per second, but it's going north. So this whole thing right here would be a vector because it has a magnitude and it has a direction. Some examples of this are displacement, velocity, but also we're going to talk about acceleration. It's going to be a vector, but also things we're going to talk about later on in the course are forces, momentum. Yeah, those are the two big ones we're going to talk about. But those are also vectors, also torque. But those are vectors, and a vector just once again has a magnitude and a direction to it. Whenever we talk about motion, it's really important to sort of understand the idea of position, distance, and displacement, because a lot of times they can be used interchangeably, and in maybe just everyday language, or if you're just talking with your friend, that's okay. But in physics, they have 3 distinct meanings. Your position is where you're located at a given time on a given coordinate system. So in this case, our car is at 4 miles. And the only reason this makes sense is because we know right here, we're saying the post office at 0. It's 4 miles from the post office, and that's our position. The position doesn't tell us anything about the system other than the fact of where an object is. It's not going to tell us where it's been, and it's not going to tell us where something's going. It's only going to tell us where something is now or at some time. Distance, on the other hand, is the length of the path traveled by an object. So this is going to be a scalar quantity. So in this case, we say here, and our distance is how far we traveled. So we go from our start to our finish, and we travel a distance, delta x, of 100 meters. So distance is just the total length of the path that you traveled. Displacement, on the other hand, is your change in position of the object from the final to the initial. So it's going to be our final minus our initial. All of our vectors we represent with an arrow on top. That's how we know it's a vector. So in this case, our displacement will be our final minus our initial, which will just be 150 minus 50, which will be 100 meters to the right. And we know it's to the right because our final position is to the right of our initial position. So that's how we determine our direction, by looking at that, how the final and initial position go. Your direction always goes from initial to final. Now in this scenario, distance and displacement are the same, but that doesn't always have to be true. Let's look at this next scenario where first, we travel 150 feet or 100 feet to the right, and we say we get there and we realize, oh my, I dropped my wallet back there 50 feet ago. Now I have to turn back and I have to go 50 more feet. Well, in this case, my total distance is the total length of the path traveled. So that's going to be the 100 feet plus the 50 feet. So my distance is 150 feet. However, my displacement is we only care about my final minus my initial. My final position is 100 feet and my initial is 50 feet. So in this case, my displacement is going to be 50 meters to the right. So always be careful about this. Your distance is a total length traveled. Your displacement is only concerned with where you started and where you ended. It doesn't matter what path you took to get there. The next thing we're going to talk about is speed and velocity, and these are two things that people use as the same word all the time. I've even made that mistake, and I've studied physics. They are similar, though, because they're both the rate of change of position. It's both how fast you're moving, and they both have the same unit in physics. They're both a meter per second or mile per hour. However, they do have major differences. Speed is your rate of change of distance. Velocity is your rate of change of displacement. And basically what this means is that speed is a scalar quantity. It's going to be your distance divided by your time, whereas velocity is going to be a vector quantity. It's going to be your displacement divided by your time. So once again, velocity it's going to have a direction to it, but it also is only concerned with our final position and our initial position. So I have a question for you guys, a scenario, and I want you to answer it in your notes, and we're going to talk about it in class. And I want to see if you can kind of catch on to what's happening. So we have two friends, Sam and Sam and Sally are smart because they're watching a jogger complete a 400-meter lap instead of, actually doing it themselves. They're very smart. Running is not fun, so I like Sam and Sally. Sam states that the jogger's velocity was 4 meters per second during this lap. Well, Sally says, no. The jogger's speed was 4 minutes per second. I want to know who's right, because one of these people are right and one of them's wrong. So go ahead, write down your notes. Who do you think is right? And we're going to talk about this more on, I guess it'll be on our next class period, which I think will be Tuesday. Now, one thing we're going to look at is we want to say, well, what's our average speed and what's our average velocity? Because those are two important quantities. They tell us what the average motion is. Well, in this case, we know that a runner goes 200 meters east, changes direction, and runs 300 meters west. The entire trip takes 60 seconds. Holy cow, that's pretty fast. Well, the first thing we're going to look at is average speed. And our average speed is our total path divided by our time. And in this case, our total path is going to be that 200 meters plus the 300 meters. So we've traveled a grand total of 500 meters in 60 seconds. That means that our average speed is 8.33 meters per second, which is pretty fast. That's a pretty good speed. Direction doesn't matter. It doesn't matter that we turned around at some point. No, all that matters is our total distance, which was 500 meters. And we traveled that in 60 seconds, and our average speed is 8.33 meters per second. Now we want to find the average velocity, though. And we know that's our displacement divided by time. Well, our displacement is our final position minus our initial position. In this case, our initial position is 0, and our final position is negative 100 meters, because we ended up 100 meters behind where we started. So we can go ahead and plug that into our equation. We find that our average velocity is negative 1.67 meters per second. And if you wanted to, we'll talk more about this in class, you could leave that as is. A negative sign can tell us what direction an object is moving. Or if you wanted to, you could rewrite that and say, well, it's 1.67 meters per second to the west, because we're heading west. You know, if this would be east and this is west. Or if you wanted to do if you didn't want to do west, you could always say to the left. So that's what our average velocity is. So our average velocity is different than our average speed, and that's because our velocity, or average velocity, is just our final position minus our initial position divided by time, whereas our average speed is our total distance divided by time. And in this case, they're going to be different because we turned around. The last thing I'm going to talk about now is average versus instantaneous velocity. Our average velocity is what we just calculated. It's that displacement divided by time. It's going to give us a number, and it's going to tell us what the average velocity is over some period of time. Instantaneous velocity, on the other hand, is the velocity at an instant in time. So it's how fast you're moving at, time 5 seconds, or time 25 seconds, or 35 seconds. That's what average velocity is, or instantaneous velocity. It's at that one point in time. And we can write it very fancy as the limit as delta t goes to 0. You don't need to know that. All you really need to know is that instantaneous velocity is at one point in time. If we ever have objects that move at constant velocity, so they're moving at the same velocity the entire trip, their instantaneous velocity and their average velocity will be the same. However, if our velocity or speed of our object is changing, maybe we speed up or slow down or turn around or something like that, well, then our average velocity and our instantaneous velocity will be different. And that'll be important to know. And we're going to talk more about this whenever we look at graphs and how graphs can describe motion. Because the graph will really show us that difference between average and instantaneous velocity. So that's the end of our video now. Everything else we're going to cover in class in notes because it's a little tricky and kind of weird. And, pluses and minuses and acceleration get kind of crazy. So we're going to talk about that in class. Now, your only thing that you have left to do is go and answer your video check question. The link is going to be on right below the video in our Canvas assignment. If you can't find it, just send me an email and I'll send you the link to yourself. But it's just going to be a Google form. There'll be 2 or 3 questions that I want you to answer. Everyone have a great night, and I will see you in class tomorrow.